just take. So thanks for the invitation. It's a great pleasure because I think I have seen many of you during my PhD thesis on thermoacoustics, and so now like I will present something a little bit different because we are focusing on artificial intelligence. So I won't go into combustion because many of our test cases are more from the aerodynamic side. And I think the presentation will complement the one just done by Corentin, where basically it shows us some application, and my goal will also to look at some application and focus on how you can complement CFD tool with artificial intelligence, how the two are complementing each other. Like for sure, artificial intelligence is not going to replace CFD. The goal is really to put the two together. And we try to show what you can do with that and what are the difficulties when you are trying to do that. And basically, Corentin finishes his presentation by saying some of the difficulty for example with time varying problem extra. So we will go through three applications if we have time. So an hybrid solver with CFD and deep learning, one with acoustic wave propagation to look at time varying problem, and if we have time to reinforcement learning part for flow control, so that you have an overview of the main topics that we do at ISAE Super on trying to apply artificial intelligence to fluid mechanics. And I want to start with a very brief introduction. Since Corentin already talked a lot with deep learning, I will try to do that as fast as possible because you already get some details about what is deep learning, what it can do extra. Just as an overview, you can see that the three videos that you can see there, they are all produced by artificial intelligence, the three you can see there. So we will try to go through this application. A very brief introduction. So I'm from ISAE Super, which is an engineering school in France, located in Toulouse, that you can see on the map. I won't go too much into the figures. Basically, the goal here is to say that we have about 2,000 students and 200 doctoral students at ISAE Super. It is quite small compared to classical universities that you have in Europe. It's still an engineering school. And inside this engineering school, I'm in the DAEP lab, which is a lab for aeronautical flow physics. So basically, we do fluid mechanics. And they are, okay, I don't know why you still see my presentation because it was kicked out.
No, we don't see it anymore.
No, I don't see it anymore.
Okay, I don't know why. Sorry for that. I was here. So we share again. Okay, I hope it works. It's fine again?
Yeah.
Okay. So yeah, we have three groups dedicated to fluid mechanics from fundamental research, so mostly turbulence and shock waves, toward external flows, as you can see here on the videos, and until turbo machinery and propulsion, so for real system, as you can see first of all on the bottom right, where you have the full engine, you have a test bench with a full engine, which is equipped with some measurements, etc. And artificial intelligence, so the group I lead at ISAE Super is really going through these different groups. Really the goal is to go from fundamentals toward application and try to understand how artificial intelligence can help at this several level of details, let's say. This is just to highlight the fact that this work is not done alone, and of course many postdocs and PhD students have helped I think now we have 3 postdocs and almost 4 PhD students working on the several applications I will just show. It also goes through many collaboration. I think it's one of the key points when you are trying to do this artificial intelligence for fluid mechanics, trying to collaborate with several groups where you can really put the ideas together. This is really the way I think we will make some change and some new to get right to new ideas by doing artificial intelligence in CFD. So I really try to motivate some collaborations. Corentin said a lot already about artificial intelligence. From my perspective, it's really a set of theory and mostly statistics. And this is what we need to keep in mind. This is statistics at some point. They're just trying to mimic some human intelligence aspects, but it's never intelligence. The word artificial intelligence is maybe not the best one to use because at the end, we will see it's a statistical tool and an optimization behind. So basically, it is going to do what you are trying to do right now, and there's very little of generalization or physical constraint, etc. They are very difficult to put into that thing. So they are not that intelligent. You really need to be careful about the data sets, the methods you are employing, and this is why I will try to show during this presentation all the difficulties that artificial intelligence can have when you try to tackle some physical problem where you want some constraint about physics, about time varying problems, etc. So Corentin really said a little bit about like the several things. So inside artificial intelligence here, at least in this presentation, we are going to focus on machine learning. Inside this, I will be more specific on deep learning and reinforcement learning. And we will see the difference between the two. For reinforcement learning, because deep learning was already a bit shown by Corentin, reinforcement learning, the best to explain is by an example. I think I will show that just after when we look at reinforcement learning. So in deep learning and reinforcement learning, basically you have 3 large types of problems. The first one is supervised learning. So basically you have your data, X, and you have already your desired output, Y, and you try to map X to Y, and so to create a model at some point. And to do that, you have your neural network, which is your model, which is predicting some output, and you compare your output with your desired output, which creates an error, and this error is back propagating to the model, where you can do an optimization with a gradient descent to optimize the weight that you have in your neural network to create at the end your model. So this is supervised learning, which mostly is used to learn to predict, basically. Another type of machine learning problem is you still have your data, X, and what you want is some output, but now you don't have the desired output. So it's unsupervised in the meaning that you cannot create this error between predicted and desired output. And this kind of unsupervised learning, which are much more difficult to train, are mostly done to find structures, cluster, categories inside your data. And the final type that we'll try to look at the end of this presentation is reinforcement, basically where you have an agent inside an environment that can do some action and get some reward. And what you want is that the reinforcement learning is able to learn how to make the good decision of which action I should do to maximize my reward. And so typically, this kind of problem is more on learning to make some decision and good decision. Neural networks, of course, you can apply them to the three types of machine learning problems, and they go most of the case in the model. And for reinforcement learning, the neural network is inside the agent, which is trying to learn to make the decision. As I said, for reinforcement, I have put here a small video so that it's, I think it's better with example. Basically, here you have a hand, and you need to program the hand so that you can play with this Rubik's Cube to solve it. And if you try to program this by yourself by saying, okay, in that position, you need to move this finger in that direction, it's just intractable. So you need to find another way, and reinforcement learning here is basically say, like, if you cannot have clue on how to control the system, just interact with it. And here you see the final stage of reinforcement learning, where basically he has learned how to solve the reinforcement learning with one hand. I can go a bit more at the end of the video, and you see he's able to actually solve the problem just by itself. So basically, reinforcement learning, as we will see at the end of the presentation, is really to learn and make decisions. And in our context of CFD, it will be for flow control or flow optimization. It helps a lot. As Corentin said already, like it's not clear if it's a hype or not, but for sure, like when you look at the article, for example, in Web of Science dealing with CFD and learning in some aspects, you can clearly see that there is a huge number of papers that now are popping up a bit everywhere. Now we are about 100 of articles in 2019, and when you look into that, you can see that just a little part are deep learning and reinforcement learning. So most of the papers, they are still on classical machine learning, I would say. And so it's still a field which is not completely mature. And this is also the goal of my presentation, is to look at difficulties and what difficulties we are facing when we try to deal with this deep learning and reinforcement learning problem. So this is what Corentin just said before. I just add the control loop here that we will look into with reinforcement learning at the end of the presentation. When you try to do that, basically to apply artificial intelligence to fluid mechanics problem, I like to cite this paper, which is a review from Brunton et al., which basically already, so it's last year, 2019, basically they highlight the difficulties of machine learning by saying that it comes without any guarantees of performance, robustness, and convergence. And so a lot of work has to be done into that direction to make them reliable, and especially when they are inside a CFD solver. If you want to trust your CFD solver, you need to trust your artificial intelligence which is behind, if you have coupled the two together. And a lot of work are still need to be done. And the other question is, artificial intelligence is mostly done for data-driven algorithm, meaning that you have some data and you create an artificial intelligence based on that. But as soon as you are doing physics, it is not just data. You also have a pure knowledge of your system. First of all, you have some equations that you can use. And so another challenge is how you can enforce some physics into machine learning problems. So it can be equation, it can be how you can enforce some symmetries, some coherence in time, etc. And so we will try to look at these two difficulties all along this presentation toward these three different applications. So the first one is trying to make an hybrid solver between CFD and deep learning for an in-computable solver. And you can see more details on this recent AIAA paper of this year, made by Eki Ajoria. So the problem is like this: we have an incompressible solver, either Euler or Navier-Stokes. It doesn't change too much. And basically, this kind of solver, you have a mass conservation equation and a momentum conservation equation. Okay, and usually you start with an advection. So you have your velocity field u. You conduct through the momentum equation, you get u star, and then since it's only use the momentum conservation equation, it doesn't satisfy the mass conservation. So you try to combine both mass and momentum, and it leads to the Poisson equation. So basically, you need to make a correction of the velocity field so that now it satisfies the mass conservation and still the momentum conservation that you had just before. So basically, the goal of the Poisson equation is from your one velocity u star is to create a pressure gradient that you can use to correct your velocity field. So at the end, you have actually the divergence of u equal to 0. And to do that, traditional solver, they are iterative methods. For suppose the Jacobi solver, you need iteration to do that. And if you want to be more precise, you need to do more iteration, and so it can be very costly. The goal here is to replace this person solver by a convolutional neural network as the one that Quentin just presented before. And the two questions we have is the one from Brunton et al. In fact, is can we quantify the error made by such a network, and how we can guarantee of accuracy, especially in time or other different scenarios. For example, if I change from one case to another, can I still have some guarantee of the accuracy of this coupled system? So for that, we are building an hybrid solver, and the first step is to train a CNN, so a neural network, to solve the Poisson solver. So to do that, we didn't want to go to very complicated data set, because I think if you try to make machine learning by always creating new data set, at the end you are spending a lot of computational time into the data set. So what we wanted here is to keep with a very simple data set which were already done by Google, in fact. So this looks like this, something very simple. You have just random geometries and random initialization through divergence kick, and it's a 2D Euler equation. And you make 100 of these cases, and you store soft snapshots. So at the end, you get about 20,000 samples of this uncorrected velocity and the pressure solution at the end. And we wanted to keep this very simple, and then look at one, if we can train a neural network to replicate the Poisson solver for that, and then how it can generalize on more classical fluid problems, typically a plum, a jet, a von Karman street, etc. To do that, we have trained several architecture of the neural networks, and we'll see that one point also of this presentation is to find methods to actually compare these several architecture. So basically here you have what we call the monoscale, which is a complete feed-forward system with just convolution layer stacked one after the other. And we have limited the number of parameters to about 400,000 parameters so to tune inside the neural network. And we have tried a more complicated one, which are called multiscale, which are close to the one that Quentin just said before with the UNets. Basically, the goal is to have several branches which are looking at several grid spacing, so a coarse one and much finest one. And for this, we have done two multiscale, one with the same number of parameters as the monoscale one, and multiscale two, which is much smaller, to see how this kind of networks is good in terms of accuracy and performance when you are changing the number of parameters you have inside. So the question we want to look at into this presentation here is how general a neural network is. So is it still accurate on new cases compared to the very simple data set we have just seen for the training part? How precise they are, so how we can measure actually the neural network error. We will see that it's not that easy to define what is the error that you need to control in a neural network. And at the end, when you have done everything like this, that you know how general they are and how precise they are, you can actually evaluate how fast they are, because you can evaluate the performance of a neural network only if they are at the same accuracy level. So first, how general it is. So we have trained the neural network based on the dataset you have just seen, and now we will apply this to a plum case. So this is like this. You have a box where you have an inlet at the bottom, and you inject with the velocity v1 and a different density ρ1, which is different than the one you have in the box. And so when you look at the parameters which is controlling this problem, you have three of them. The Reynolds number here is infinite because it's Euler equation, so you have no viscosity. The density ratio is very small because we are using the Boussinesq approximation. So basically, Reynolds number and density ratio, they are not evolving. However, this problem is parameterized by the Richardson number, which controls the buoyancy force and the flow shear. So basically, the effect of the jets and the buoyancy, which are the two ways that makes the plum move into that box. And so we will look at several Richardson number, how our neural network is able to replicate the physics. Knowing that the learning dataset, so the training dataset, was done at Richardson equal to 0. There were no difference in density. So we have a training data set which has done at Richardson equal to 0, and we will see what happens when we try to use that neural network for cases with higher Richardson number, so not 0, and see if it's able to generalize to new physics, basically. So this is what you have at very low Richardson number, so close to the training data set. You have this term which is rising. On the left, you have the classical iterative methods, which is the Jacobi method, and on the right, you have the neural network. And you can see that globally, you are replicating correctly the physics of the plane. The problem is if you increase the Richardson number, you will see that some problem will arise. To quantify more accurately this good behavior of the plum, we can look at the head position, so in time, so the top of the plum. You take this height and you look at how it evolves in time, and basically you can get this chart, and you can see that the Jacobi methods, you need at least 200 iterations so to make it converge, and you can also see that neural networks is at the end able to replicate very accurately this physics of how the plum is rising into the box. Now, if you compare the performance of the neural network compared to the Jacobi methods, you have like this. So here we have the Servo-Jacobi method and the neural network, and we are looking at the time to compute the simulation compared to the time needed by the neural network. So one is multiplicative, and the other one is so the first column, is just for the Poisson solver, and the other one is for the complete iteration of your solver. So what you can see here is like when you are looking at a Jacobi solver, they're taking a huge time to solve this Poisson equation. Typically, you need almost 80% of your time by just solving the Poisson equation into your Poisson solver. So it's really a bottleneck, and if you are able to leverage this, you can really get a significant speed up. And this is what you can achieve with your neural networks when you compare Jacobi 200 and neural network, which have almost the same performance. You can see that you get almost 250 times faster method. It's not in percentage, the green one is really 200 times faster, the method, which makes that your coupled approach, where you have CFD plus the neural networks to solve your Poisson solver, now the Poisson equation is just 2% of your computational time. So you have a method which is able to really reduce this bottleneck a lot. So as I said, this is for a low Richardson number. The main problem is, as you can see here, when you look at higher Richardson number, it doesn't really robust anymore. So this is for almost Richardson 1, and if you go even higher, basically the simulation is completely unstable because of the numerics, the neural networks making everything unstable, and at the end it crashes. So this is one of the last remark of Corentin, where I was saying like this is one of the crucial question we have, how we can make neural networks inside time varying problem and time varying solver, making stable and accurate in time. So here we try to propose a method, which basically, if you want to improve this result, you can improve the learning, make a new data set. But as I explained, we didn't want to do that, because if you have to redo a data set for each new cases, at some point there is no point to do artificial intelligence. Just compute directly your new case with your classical CFD solver. So here we try to go to an hybrid approach where we couple CFD and deep learning together. So it's the same scheme as before. The only thing is when your neural network is now predicting a pressure, you make the correction, you get the divergence. And then the simple idea is, depending on the threshold of this error, if this error is low enough, you compute the next step. If it's not enough, you hybridize your neural network and you just make new Jacobi iteration by using your neural network's prediction as initial guess. And you see if you have some gain in terms of robustness, and if you are still having a fast incremental solver doing this. And this is the results for the highest Richardson number we have seen, where before it was completely unstable. And just here, by making an hybrid approach where Jacobi is also helping at the end the neural network to get the solution. We have something completely stable in time and with the correct physics in terms of head position in time. On the red, you can see that the additional cost that you have when you do this hybrid solver compared to the neural networks we have is just 5%, which is almost nothing. So at the end, you still have a very, very fast incompressible solver, but now with some guarantee of the stability and accuracy of your system. If we look a little bit more at this question of accuracy, what I wanted to look at is what's the error that we really want into a CFD. In fact, when you look at neural networks, it's easy to look at the error done during the training, which basically here is based on the divergence of the velocity field. So you look at a maximum or a mean or any measure of that. But at the end, this is not really what you want. At the end, what you want is to actually have the correct physics. And so it was not clear what is the errors that you need to control for the neural network to get the right physics, so to get the right head position in time. And so we use this hybrid approach with the three architecture of neural networks that I've presented before and the Jacobi solver. And so we try to follow, because with the hybrid solver, we're able to actually control the error we made. And so we base the threshold either on the max of the divergence of the velocity field or the mean of the divergence of the velocity field. And you can see on the left that when you try to follow the max, so when you try to control the maximum errors that you have in your CFD domain, at the end, all the methods, they behave very differently. However, when you try to enforce the same mean error for the divergence of the velocity field, all the methods, they are doing the same. And you can see the head position in time, they are exactly the same. So basically, the physics here, at least for that case, is controlled by the mean divergence field. And I will go really quickly to that. Basically, what you have is when you are following the max or following the mean, you are not constraining the error the same way. And basically, you can see that the max here is just like 1 pixel in your CFD domain. This is not where you do all the loss of the mass that you have in the system. If you want to control the system, the mean is more representative of the mean mass that you are losing over the CFD, and this is the one that you need to control to have the right physics. And so now that we can, with the hybrid approach, having exactly the physics we want, so we can compare all architectures, all the Jacobi methods to have exactly the same physics, so to have exactly the same head position. And this is what we get. On the left here, we look at the hybrid methods, where we look at how many iterations of the Jacobi solver we have after the neural network. So here, with the square, it's just the Jacobi method itself. You can look with the several architectures that, in fact, when you are using a neural network, it helps to reduce a lot sometimes this number of iterations that you can do of the Jacobi solver. And typically, the multiscale with 400,000 parameters is very accurate, and you almost need no Jacobi iteration to solve your problem. And so this is at the same accuracy level. And so now you can, again, evaluate more precisely the performance of your network. So it's the same chart as before. Instead of here, it's based on the same physical error. Compared to before, it was the same divergence field error, let's say. So some more a neural network error. And here, at the same physics, you can still see that it's compared to the multiscale network. The Jacobi is still 70 times longer than our neural networks. And by changing the architecture of the neural network, you can have very different results. And typically, even the multiscale network, which was a very smallest one, so as you can see on the left, is less accurate, you still have a significant speed up. So even with small multiscale, you can achieve some speed up compared to classical methods as the Jacobi solver. Just to finish very rapidly, we try to do exactly the same as the plum case I have shown you, but with the von Karman split, where it is now controlled by the Reynolds number instead of the Richardson number. And the same, during the training, it was an infinite Reynolds number. And then we will look at a low range of Reynolds number, typically from 100 to 1,000. to see if all the methodology we placed is still apply on this new case, very different compared to the training data set again. And this is a result. You have on the bottom line the Jacobi solver, and on the top one, the one with the neural network at several Reynolds number. And what you can see here, and is like with this hybrid approach, we're able to really replicate all the Reynolds number of these simulations with the right physics, the right fluctuation of vorticity behind the cylinder, even if the training phase was done with infinite Reynolds number. And still, we still get a very nice performance. The neural network here on the top line is, at least the Poisson solver, is about 40 times faster than the classical Jacobi solvers that you have on the bottom line. So here we try to look at an application to guarantee some error and some accuracy of the CFD coupled with the deep learning framework. But the thing is, the Poisson solver was steady, in fact, and time variation was done by the advection part, which was still done with the classical methods. So we wanted another application where now the deep learning has to deal with a time varying problem, and for that we choose an acoustic problem. So I'm not going to go into the detail, but you know it is difficult to propagate acoustic waves over long distances, mostly because you have dissipation because of your numerics, and so you need very good dissipation and dispersion properties. And so usually it leads to very high CPU cost for acoustic simulation. So we are looking at two applications of acoustic waves because we want to focus on two different problems. The A is really propagation in time, so you take a closed box and you put some Gaussian pulse that will propagate and always stay in the box because you have wall everywhere. And so you can try to look at the error in time for very, very long runs. This is a way to look at how neural networks are able to predict in time some physics. And we will look at three different test cases. One which is just a Gaussian pulse really close to the training data set. The other one is more like a dipolar source term when you have a negative and a positive Gaussian pulse very close to each other. And the next one is a planar wave to look at how general it can be, since the training set here is always done with Gaussian pulse, so with this circle shape, and he has never seen during the training this kind of planar acoustic waves. So this is why we've chosen these three different type of cases to look at several generalization of the neural network. And then we'll go to a different problem, which is now a free field propagation of acoustic waves, to focus more not on the propagation in time, but propagation through objects. So look at the scattering of acoustic waves by objects. So the training data set is done by LBM to have a very low dissipation properties. We have done 700 simulations for the training, and we keep some of them for the validation case. And for each simulation, we store some pressure field. And the goal is really to make a neural network to predict the next time step of this acoustic problem. So of course, we validate our LBM approach with some analytical formula. And you can see here a typical example of a data set where here we have 4 Gaussian pulses which are propagating inside this closed box. This is the scheme of the procedure we want. So we are using 4 time steps as input. So 4 time steps with the pressure field, and the neural network has to predict the next time step. Okay, the prediction. For that, during training, we need to have the LBM with the true snapshot to compare the two, get the error, and optimize the neural network. Once the neural network is trained, we just use the neural network in a recurrent mode. When you have 4 snapshots, it predicts the next one, and you use the next one as an input again, and so you can time marching your neural networks like this. And so the goal here is to look at if we can predict the next time step and for how long we can do that. And we also add an additional constraint, which is if we want some speed up, we will try to do that with a timestamp for the neural network, which is much larger than the one used in the CFD. So here, for example, is 3 times the timestamp we have in the LBM case. The neural network is close to the one that I presented for the incompressible solver. It's a multi-scale convolutional network. And here, what I want to focus on is the loss function, so the cost function, which is used to optimize the neural network. And here we have several ingredients. Basically, in the error, we'll use a mean square error on the pressure and on the gradient. We are using the gradient to make a prediction sharp. And we will look at the effect of trying to make what we call a long-term loss. Since here we really want that the neural network is able to predict in time and for a very long time, we'll look at this approach by usually the short-term loss is just you are outputting the next time step and you create the error based on the next time step. And you are hoping that accumulation of error is not too bad. By long-term loss, basically, when you will optimize your neural network, you will output the next time step and a few of them at the end. And you back propagating your error after, let's say, 4, 10 time steps. And so basically, it should give to the network some information about how, what the error I can do and what the error I should not do. Typically, some errors are going to accumulate a lot and create a lot of errors at the end. And part of the error at the end is not really propagating in time. So long-term loss is really trying to put some information about how the error will accumulate in time and how you can constrain this to have a better result for a very long time simulation. These are the results. So this is a dipolar kind of test case. Case B, top, you have the neural networks which were trained with a short-term loss. And on the bottom one, you have the one with the long-term loss. And basically what we can see here, even on this very simple test case, that when you add this constraint of trying to predict during the training phase, like when you try to enforce this long time accuracy of your network, it helps a lot. It also helped doing some generalization. Here, everything was done with Gaussian pulses. And when we switched to planar waves, you can see that very rapidly, the classical neural networks is diverging from the LBM solver. And just by getting this information of what the errors the neural network will do on the long run, it helps a lot to stabilize the system. You can see that it's much better on the bottom line than on the top line. Yet we can still see that it diverges at some time, and we still have this error, which is basically drifting in time for very long simulation. So this is one way to mitigate this error. The second one that we have to put in place, in addition to the long-term loss, is to put some physical constraint as well. So typically, the prime of the acoustic pulse in the box, we can say that the acoustic energy should remain the same. And so we are not redoing the training set here, but just after the prediction of the neural network, we are making a correction of the prediction by saying the prediction you do now that should also satisfy the fact that the energy of the acoustic energy should be conserved. And when you do that, without retraining, you get this. So it's exactly the same case. On the left, this is a dipolar source stem. On the left, this is a planar wave. And you can see that now you are able to really have an accuracy in time either for very, very long iteration here until 400 time step, for example. If I go more quickly on the scattering objects, so this is the validation of the case with analytical, so I'm not going to go too much. So we do the same. We train with the data set with just Gaussian pulse and random geometries, and we look at how acoustic waves are scattered by objects, knowing that now is no more reflecting walls that you have on the square domain, but a free field propagation. This is a training, and typically you have some difficulty, no more because of the time varying problem, but because you need to constrain your neural networks to do a good job at walls, typically to have no porous walls extra. And it's also more difficult to put some energy preserving correction as we have done just before, because now you have no new fluxes at the boundary. yet. If we look at some validation cases, this is a Gaussian pulse and a cylinder as an object, and you can see on the LBM on the left and the neural network on the middle. That's the two simulation have a very good agreement between the two. Still, we can see a small distortion of the wave front and a small loss of symmetry, especially close to the external boundary condition of the CFD domain. If we try to go to a little more complex case, we wanted to look at wave propagation through a kind of nacelle representative of an engine. So we tried with these two NACA profile that has never been used during the training dataset. During the dataset was always cylinder and square. So on left, again, you have LBM. On the right, you have the neural networks. And what you can do is what you can see is, again, neural networks is doing a pretty good job. Typically, you have this kind of duct mode, trap modes between the two NACA profiles that is able to be replicated by the neural networks, which was not that straightforward when we look at the training dataset, where it was just a free field propagation with some obstacles at some point. Still, we still have some unphysical behavior, especially near walls, where sometimes we can see some acoustic waves going through this wall, and again a small loss of symmetries. These are still some difficulties we are trying to face right now. Just to get a few minutes to finish on that by a small glimpse at what reinforcement learning is doing. This is, I think, our most recent application. And I think clearly reinforcement learning is much more difficult compared to classical deep learning, because as we said, the spirit is very different. You will see that we have no more target to look at, so it's not a supervised learning. It's really trying to make some decision in an optimal way. So you don't know this optimal way at the beginning. You need to reconstruct this one. And so the problem of learning is much more difficult. So the basics of reinforcement learning is you have an agent, which is inside an environment, for example, here. And you can do some action. For example, go up, go left, etc. And your goal is to get some reward. Okay. So you have a state. This is your location in the environment. And the reward is when I do an action, for example, I get closer to the end of the environment, and so I get a higher reward. And the goal of reinforcement learning is to find the sequence of action that maximize this cumulative reward. So if we look at this simple problem, for example, a small environment problem where you try to look at the green case and not falling into the red case, we still have some action we can do, and the reward can be a good reward when you are on the green case and a bad reward when you are on the red case. And this is how reinforcement learning is doing. So you try to maximize a cumulative reward. So what you want is not just a reward that you will do after your action, because this is quite a simple problem, but it's when I'm in a certain state, and I do this action, I want to see how I can expect as a final cumulative reward in time. So over all the next action I can have following the strategy, so what we call this the policy that we're trying to establish. The goal on reinforcement learning is we're trying to find the good sequence, so the good strategy to solve the problem. This cumulative reward, most of the cases, is done with a discounted factor gamma, which is just to make this sum finite, and also to say that the rewards that you can get at the closest time step is much better than the one you can expect in the very long range. So basically, the sooner the better. When you have this cumulative reward, you can create a Q function, which is basically the expectation of this cumulative reward when you are in a state S. You are giving an action, A, and you are following your strategy until the end of the game. And so if you are able to fill this Q table, in fact, the problem is simple. If you know for all the policies, so all the strategy possible in this Q table, you just have to find the policy which is maximizing this Q function, and so you get your optimal strategy to solve the problem. And this is done, I'm not going to go into the math, but this is done through the Bellman equation, which gives you a way to make an approximation in an iterative way of this Q star function, so the optimal Q function that you want. And again, if you know this Q function, you know which policies or which strategy you need to follow. The problem is when you look at the literature, you can see that many algorithms exist to tackle this kind of reinforcement problem. They all share the same thing, is that they are always model-free. So it means that you're actually interacting with your system. You don't need to do prior that a kind of approximator of your system with some assumption extra. So you can directly interact with that. And here we will also focus on what we call continuous state and space action. So if you look at the Q table we have just seen before, you have the state and the actions that you need to fill into the table. If it's continuous, it means that the state action and the space action is just an infinite number of rows and columns. So it's much more difficult to tackle the problem. And this is where neural networks are coming into the game. Basically, neural networks, they are here to approximate this Q function. And so if a neural network is able to approximate the Q function, I can get at the end my optimal strategy, really as before, by taking the maximum over all the policies that I want to have. We have tried this reinforcement algorithm on a very simple problem for which we can have for which we can complexify a little bit the problem. It's a prey catching problem. So basically, the simple idea is you go from A to B, and here we enforce that we want the minimal distance possible. So the reward is really trying to go basically in a straight line for this case, from A to B. And it will be used to validate the reinforcement learning approach to see if we are actually able to learn an artificial intelligence to go from A to B. To do that, we are not actually solving this for this bird, but for a flat plate with some first analytical formula. So basically, you are looking at the mechanical equation, and what you need is to have the drag and the lift coefficient. And for that, at least here we do some assumption and get that from a semi-empirical formula or from completely analytical solution. So basically, we have a toy problem which is very fast to run. So we can do many simulations to evaluate reinforcement learning and the several parameters that control this kind of learning approach.
Michael?
Yeah?
We have a few more minutes, but we're running out of time.
Okay. Okay. So I can go quickly on the results. You can see here we go from A to B, and this is along the learning path. He trying to go to the straight line, so he's able to learn. And you can see on the right that the cumulative reward is actually evolving along the episode, so along the time he tries to do this path. So I'm not going to go into detail for that, but basically is when you try these methods, it's not very robust. So there are still a lot of work to do in reinforcement learning. This is the idea of path. What I wanted is to look at, we try now to couple this reinforcement learning with a true CFD solver to get rid of this assumption. And we are able to do that by coupling star CCM plus with deep reinforcement learning. And you have, for example, here a video where the profile here is able to be moved by reinforcement learning to go from A to B. And we can do this with very different scenarios from A to B points like this. And you can see that all the time is able to reach the final point. And here we wanted to look at the sensitivity to the mesh, for example, to this optimal strategy. So basically, with reinforcement learning, you're able to make an optimal control or almost an optimal control of airfall or fluid. So this is my conclusion. So very general speaking, like deep learning and reinforcement learning, I think they still have a huge potential on many problems, and there are still many things to discover. But yet I think it's important to keep in mind that it's not yet really mature, and we need to adapt this to our physical problems, and I'll try to show you how we can do that. And for sure, we need some collaboration on that field to put as many ideas as possible to tackle the several difficulties we have seen.
Okay, thank you, Michael. Well, I think the reliability